Hi, my name is Michael Hind, and this is work with my co-authors Dennis Wei and Yunfeng Zheng. This paper is a detailed evaluation of an explainability framework we call TED. The motivation for the TED explainability framework is that there are very different types of explanation consumers, and thus, no one explainability technique will be able to satisfy them all. Instead, with the TED framework, we provide, during training time, examples of appropriate explanations for each training instance, in much the same way a senior employee trains a new employee by telling them what actions to take and why the action is appropriate. In this way, we are teaching the model not only how to make good predictions, but also how to generate meaningful explanations for each prediction. So the TED framework takes in a data set with features, labels, and explanations, and creates a classifier that can predict labels and explanations given an unseen feature vector. There are many possible instantiations of this framework. This work will explore a simple Cartesian product approach, which is available in the AI Explainability 360 open source toolkit. The Cartesian product instantiation of the TED framework simply merges the Y labels and E explanations together to form a new label. This label is then used with the original features to train a new classifier that will predict the joined Y and E labels, which then can be decomposed once a prediction is made. The approach can use any standard multi-class algorithm. The initial paper showed the technique to be promising for predicting Y and E, but left many questions. This work addresses some of these questions. First, since we are changing a binary classification problem into a multi-class one, how does this impact the predictiveness of Y? Next, what happens when we increase the number of explanations, i.e. the number of classes in the problem? How does the accuracy affect it? And finally, since the framework can use any multi-class algorithm, does the performance differ for different algorithms? These graphs show the difference in Y accuracy between TED-C and the base model for 2 different data sets and 4 different algorithms. For all algorithms except for light GBM, the Y accuracy of TED-C is the same or better, 0 or a negative difference, than the base algorithm. This is true even as we increase the number of explanations and classes to around 30. These charts show how the raw accuracy of both Y and E varies among algorithms and as the number of explanations increase. Here we once again see consistency with all 3 algorithms, except for LGB. We next ask what happens if the explanations contain inconsistencies, which would occur if a human gave the wrong explanation in a training data. We would expect this to confuse the model, as it is being taught incorrectly. The results confirm this for the FICO dataset, but do not show any degradation in accuracy for the employee retention dataset. Our final question addresses one of the limitations of the TED framework, that it requires explanations for every training set instance. Here we allow missing explanations on some instances and impute them from the instances with explanations. We then determine what fraction of the training dataset needs to contain explanations. Surprisingly, the algorithm's performance is consistent, even when as little as 1% of the explanations are present. The goal of this work was to identify the limitations of the TED-C instantiation. Given its simplicity, we expected it would not perform well with large number of explanations or with missing training explanations. The results were a pleasant surprise and warrant further exploration of this approach in real use cases. Please read the paper for further details.